You are sitting by the window, somewhere above the ocean. The cabin is calm, the engines are steady, and the map says your plane is moving at 560 miles per hour. For a machine carrying hundreds of people, that sounds astonishing. But then the question creeps in. Humans have built rockets that tear into space. Fighter jets can outrun sound. Concorde once crossed the Atlantic in about half the time. So why is this modern airliner with all its technology still moving at a speed that would have looked familiar decades ago? Why does commercial aviation seem to stop just before it becomes truly fast? The answer is not as simple as fuel, engines, or airline caution. It is hidden in the moment air stops behaving the way we expect. Let's get into it right here on Secrets of Simple Things. It is not an engine problem. The easiest mistake is to imagine an airplane like a car. Push the pedal harder, the engine works harder, and the vehicle goes faster. A jet can feel similar. Throttles forward, engines roaring, aircraft accelerating. But an airliner is not choosing between slow and fast. It is flying inside a protected speed window. At the lower edge, the wings may no longer make enough lift, go too slow, and airflow can stop staying attached properly. At the upper edge, air around the wings turns violent. Control surfaces become less predictable, and the structure feels loads it was not designed to carry. Many modern airliners have enough thrust to go faster for a short time, but more thrust does not create a larger safe speed window. The engines may have more power, but the aircraft does not have more safe speed to give. To see why, start with the simplest enemy every moving object meets: drag. The faster you go, the harder air fights back. Drag is easy to feel. Roll down a car window and hold your hand outside. At a gentle speed, the air feels soft. Drive faster, and the same invisible air pushes your hand backward. Faster still, and it begins to feel almost solid. That is the first lesson. Air may be invisible, but speed gives it weight, and drag does not rise politely. Roughly speaking, double your speed and drag can become 4 times stronger. Triple your speed, and it can become 9 times stronger. Now scale that from your hand to a passenger aircraft weighing hundreds of tons cutting through the sky. To fly much faster, the aircraft does not need a little extra fuel. It needs much more energy to push through air that is fighting back harder every second. But normal drag is only the beginning. Near the speed of sound, air does not just resist more. It begins to behave differently. That new resistance is called wave drag, and this is where the real wall begins, the transonic zone. The invisible wall near Mach 1. Mach 1 means the speed of sound in the surrounding air. The number changes with altitude and temperature, but at sea level it is roughly 767 miles per hour. Sound is a pressure wave, tiny pulses of compressed air spreading outward. An aircraft creates pressure waves too. At lower speeds, those waves travel ahead of the airplane, giving the air time to shift and flow around the body. But as the airplane gets closer to Mach 1, it begins catching up to its own pressure waves. The air ahead has less time to move. Instead of smoothly parting, it compresses. Pressure builds. The invisible air in front becomes harder to push through. This is not a brick wall. Nothing appears in the sky. But physically, the airplane has entered a place where air stops behaving like calm space and starts behaving like something crowded and unstable. That region is called the transonic zone, roughly around Mach 0.8 to Mach 1.2. But the strangest part is that the airplane does not have to reach Mach 1 for parts of it to experience Mach 1. The wing reaches trouble before the plane does. A wing does not simply pass through air, it changes the air. As the aircraft moves forward, the wing guides airflow around it. The air moving over the upper surface speeds up compared with the air below. That pressure difference helps create lift, the force holding the aircraft in the sky. At high subsonic speed, that same effect becomes a hidden problem. The airplane itself may still be below Mach 1, perhaps flying at Mach 0.82 or Mach 0.85. but the air over the top of the wing is already moving faster than the aircraft. In small areas, that airflow can reach Mach 1 before the plane does. The aircraft has not broken the sound barrier, but parts of the air around it have. When that local airflow goes supersonic and then suddenly slows down again, shock waves form on the wing. These sharp jumps in pressure disturb the smooth stream of air the wing depends on. The airflow can separate, turn turbulent, and stop behaving cleanly. That is when the aircraft may begin to buffet. The wing can shake. Lift becomes less steady. The control surfaces may lose authority. Pilots call this warning Mach buffet. The plane does not need to go supersonic for trouble to begin. Only part of the air over the wing does. The real limit is the airframe. So the real speed limit is not written inside the engine. It is written into the shape and strength of the airplane itself. Commercial jets fly high because thinner air means less drag and better fuel economy. But at around 35,000 feet, high-speed Mach effects also become harder to ignore. Every part of the airplane is designed around forces it is allowed to carry. The wing roots absorb enormous bending forces. The fuselage skin, spars, hinges, fasteners, and control surfaces all have limits. If the aircraft is pushed beyond its certified speed, shock waves grow stronger, airflow becomes more disturbed, and structural loads rise. The engines might still push for a moment, but the aircraft would be leaving its safe operating zone. That is why pilots have a maximum operating Mach number. It is not a suggestion, it is the upper edge of the aircraft's certified speed life. A commercial jet is not slow because it lacks power. It is careful because every part of its body has a certified limit. Why 500 to 600 miles per hour is the sweet spot? That raises the next question. If faster is dangerous and expensive, why do airliners fly as fast as they do? Because a passenger jet is also part of a schedule, a business, and a transportation system. If it cruises too slowly, trips take longer, crews spend more hours in the air, and aircraft complete fewer flights in a day. There is also an aerodynamic reason. At lower speeds, the wings still support the same heavy aircraft, often at a less efficient angle, creating drag in another way. But faster is not automatically better. Push too close to Mach 1, and drag rises sharply. Wave drag appears. Shock waves disturb the wing. Fuel burn climbs. The ride can become rougher, the controls less comfortable, and the structure more heavily loaded. That is why the familiar 500 to 600 miles per hour range exists. For many modern wide-body jets, cruise sights around Mach 0.85. It is fast enough to make long-distance travel practical, but low enough to stay away from the dangerous edge of transonic flight. This is the sweet spot where physics, economics, comfort, control, and structure all meet. Speed has a hidden maintenance bill. Even after the flight is over, that speed decision is still affecting the airplane. Every airliner has a life measured in cycles. One takeoff, one climb, one pressurized cruise, one descent, one landing. That is a cycle. During each cycle, the aircraft changes slightly. The fuselage pressurizes, the wings bend, the skin, fasteners, hinges, panels, and internal structures all carry repeated loads. One flight is not enough to damage them, but over tens of thousands of flights, tiny stresses matter. Flying faster makes those stresses larger. It does not only burn more fuel, it increases aerodynamic load on the wings, fuselage, control surfaces, and the parts holding them together. Those loads can shorten inspection intervals and make components reach replacement limits sooner. For an airline, a small increase in cruise speed across an entire fleet is not just a few minutes saved. It can become more fuel, more inspections, more repairs, and less useful life from a very expensive aircraft. Speed carries a bill that does not always appear on the fuel receipt. Why fighter jets and Concorde are different? If speed is so costly, how do fighter jets and Concorde break the rule? Fighter jets are built for a different job. A military aircraft may need speed for interception, combat, escape, or short bursts of extreme performance. It can accept trade-offs a commercial airliner cannot. When a fighter goes supersonic, fuel disappears quickly, range drops. The skin heats from air friction, materials expand, every surface is pushed harder. That kind of speed is useful, but it is not gentle. It is not how an airliner wants to spend hours crossing an ocean. And then there was Concorde. Concorde proved that supersonic passenger flight was possible. It crossed the Atlantic at about Mach 2 and cut travel time dramatically. As an engineering achievement, it was extraordinary, but as mass transportation, it struggled. It carried relatively few passengers. It burned a huge amount of fuel. Tickets were expensive, and because supersonic flight creates a sonic boom, it was heavily restricted over land. So the lesson was not that passenger jets cannot go supersonic. They can. The harder question is whether doing it makes sense. Modern airliners are not stuck in the past. They are sitting at a carefully chosen compromise. The plane is not slow. It is optimized. Now return to that flight tracker. The number still says 560 miles per hour, but it should look different now. It is not proof that aviation has stopped advancing. It is the result of decades of aerodynamics, materials, economics, comfort, and safety, all narrowing toward one answer. A passenger jet can sometimes be pushed faster, but in normal service, it should not live there. Near Mach 1, air changes its behavior. Wings meet shock waves, structures carry heavier loads, fuel burn, maintenance cost, and risk all rise. So the aircraft is not being held back by a lack of imagination. It is flying at the speed where the whole system works best. The real achievement is not making a passenger jet as fast as possible. It is knowing the exact speed where it should stop. If this story changed the way you think about airplanes, subscribe to Secrets of Simple Things. Because sometimes the most impressive engineering is not about going faster, but knowing the exact limit where speed, safety, and physics must meet.